Can you see anything that's being lit?
Barely. I feel like
Let's change the lights. Okay. Let's do this. I'll just start working on the board because you can't see anything.
okay.
And that's absolutely pointless. See, like, if I do stuff like
I think you can
this.
see it well. It doesn't matter.
Well, I mean, if you can't see it, that's absolutely pointless to do it. So let's just work on the whiteboards, and I'll let them know to, I don't know, change the lighting in here. Or maybe there's a setting for brightness on this. I don't know. That's all. Well, I'll tell them. Okay, let's do this. All right, we'll just use old school whiteboard. Okay, let's just use whiteboards for now. Okay, what's the question?
You know what, I'm gonna start with the one with the highest points. Just the switch in the current.
Okay, do the one. Okay, which one do you know?
Which ones do I know?
Yeah, out of how many questions are there?
8.
Out of the 8 ones, how many do you know? Like, do you know for sure that no problem? To some fair extent, not like 100%, but like.
I understand V equals IR, the one with the current, electric current.
V equals IR, okay.
I understand that one.
That's what, number 1?
Yeah.
So number 2 is very similar.
I mean, Kirchhoff's law, it's.
That's the one where you have to make the loops.
Yeah.
Okay, we have the equations. Okay, and then?
Number 3, I mean, I understand the concept of RC circuits.
Okay.
It's just that there are some circuits that can be kind of tricky.
Yeah, some circuits take some time. Okay, what else? So what question do you want to start off with?
I'd like to go with the, I'm going to start with the first one.
If you're good with that, do something with what you're not comfortable with.
I'm not comfortable with magnetism.
Okay, so let's do that.
It says an electron moves from point A to point C within uniform magnetic field as depicted below.
What number is this?
4.
Okay. All right. All right. So let's. All right, got that. And you have the 3 points, A, B, and C. And C, right? A, B, and C. And they say you go from A to C.
Mm-hmm.
So all you know is you're going in this general direction.
Right.
Okay. So what I don't have my equation sheet on me, which is, but to find the force, right? You take your fingers in the direction of the, well, for you, it'd be like this.
I mean, well, I'm fine using my right hand.
Okay. So you take your fingers in the direction of the velocity, right? So the direction when it initially starts off, and you curl your fingers in the direction of the B field.
So the B field is pointing into the, well, because the X is.
Yeah.
So it's like super like this.
So you go like this, up, right?
Yeah.
So. Hold on, let me remember this. So you want the direction to be that way. So they're asking what's the force, right? So
Yeah.
Okay. So you're moving in this, you're moving in that direction, right? Close to right. Okay, and you're moving up.
Yeah.
So you do the right, right, into the board, because that's the way the leaf is going. And you get your thumb going up.
Yeah.
Which is the direction you want it to go in. Right? So I believe that the general direction of the magnetic force on the electron, oh wait, so the electron? Oh no. Okay, then it's flipped.
Yeah.
Okay, no. If it's an electron, then essentially your B field is coming up, right? You just switch the direction of your B field,
Yeah.
it's an electron, or you use your left hand in this case. So for an electron, if you want to go up, if you go, left, and you go up, yeah. So for the electron, then the force will be coming to the left. Right?
Okay.
Yeah, because then the left into the board.
Oh, yeah.
Right? So I believe its force is to the left.
Okay. Forces the magnet force to the left.
I think so, yeah. Hey, what's up? Can I get your name, please?
Yeah.
I don't have I forgot the paper, so I'll just add you there.
Okay.
But just tell me your name.
Do you want last name first?
First name.
All right, Jessica. Jessica Park.
So we're doing exam 2 that you post on Blackboard.
Okay.
We're doing spring semester 14, the green one.
Okay.
Okay, Tony?
Mhm.
Thanks. I believe that's right. Okay, so assume the distance between A and B is 4.5 meters. Right? And the momentum of the electron so you have this distance, the 4.5 meters. Right? You're given a B field of 3.2 millitesla. And you're given a momentum for the electron. The momentum of the electron is 1.15 times 10 to the negative 21. Yeah. 1.15 times 10 to the negative 21 kilogram meters per second. Yeah. Okay. You can use the momentum to find velocity.
Yes.
Okay. You don't have the equation on me, so can you tell me if you have any equations that relates to momentum and velocity? I think it's just mass and velocity.
I think you get rid of the. Oh.
Well, okay. You want to end up right. Force is equal to V cos V, right?
Right.
Velocity across the V field, right? The force. And so they're asking what's the magnitude. Oh, they're asking what's the path taken by the electron. We are working on exam 2 from spring 14.
Exam 2?
Yes, the one that's next to it.
Okay, I have it.
The
Equation sheet. Yeah.
He posted exams on Blackboard. Yeah, I just found out.
He put it up since beginning of semester.
Really?
Yeah.
Is this the one that has solutions or no? It doesn't have solutions.
No solutions.
Okay.
Okay, everybody there?
What about no solution?
Hmm.
Which number are you?
Number 4. Okay, I'm going to do a quick recap of the first one. So what's the general direction of the magnetic force on the electron? So remember, this is an electron, not a proton, right? So if it was a proton, you can regularly use the right-hand rule. But with the electron, everything's going to be flipped, right? Because the electron sign is different, it's negative. So normally you say, okay, it's going to the right to get to C. It's going in this direction, right? So then you would just do this into the board and you get up. But remember, this is the electron. So it has to be, okay, just use your left hand and left hand. It makes it a little easier because it's flipped. So the left into the board and up. So the electron, the force would be acting to the left. Yeah?
Okay, you said left for, I'm still concerned, I'm still don't understand why is it left though?
Because it's an electron.
Okay,
So if this was a proton, then the normal right-hand rule would apply,
okay,
right? But because it's an electron, the sign is different. Essentially, your B field flips because the sign is different. It's negative,
okay,
right? So instead of using the right hand, you can just use your left hand, and that will work for an electron. This is like the homework problem you guys had that looked something like this. If anybody could pull it up. We had 2 sections. We had one coming in like this, took a path like that, came here, took a path like that. So remember that one?
Mhm.
This
Oh,
is sort of similar like that. Fairly similar to this, like that. We're going here. Now you just need to know if you're traveling like this or like this. Okay, so that's what question 2 is asking. It's asking, draw the approximate path taken by the electron within the sphere. Right? So does anybody know how to do that one? Yes, no, maybe so.
For the first problem, do you need to, so it's directly from A to C, or you need to go from A to B and B to C?
It says from A to C. It says
Just
towards
directly-
C.
oh,
So I'm going to assume it just goes either something like this or something like that. It doesn't say anything about B.
Okay. So since it's electron, you use the left hand?
Yeah. Okay. Like so, for proton, you use your right hand.
Yeah.
But and then for an electron, either you can use your right hand and flip it, or you can just use your left hand and flip it. So for right hand, like if this was a proton, it'd go like this because this is the velocity, right? Like having, we're finding the direction of the force. So it's going to the right because you know that some velocity, somehow, some way, it's going to the right and up, but that's a different story. It's going to the right, and the B field goes in, so you know that it goes up. But but because it's an electron, either you can go like, you go like this, up, and but then you know it's down, or you can just use your left hand and go. Sorry, no, it's to the right and down. So I think.
The force is going down.
Yeah, I think the force is going. No.
You said left earlier.
Yeah, I made a mistake. I think, yeah, Tony, I'm sorry, I think it's down. I made a mistake.
one mistake.
Um,
So I'm correct in the first place?
when you said down?
Yeah.
Yeah, I think you're right. Yeah,
So,
because
so it's right.
it's the force would be down.
For an electron.
for the electron.
Okay.
Because it's going, the general velocity is to the right, and you cross into the field because it's the x, right, and down. So that's your force. I know it's a little weird to think about how that would work, but how a force can push down and then it goes up. But remember, this is an electron. Like, it takes a weird curvature path.
So this is, so you drew the path on how it would travel.
This is either or. Either it can either go like this from
Okay.
the outside, or it can go like this from the inside, like over here.
Okay.
Either it can go like that to get from this point to this point, or it can go like this, or like that. Right? So it just depends on which way the B field is directed, and which way the velocity is directed. So in this case, you had the velocity coming in, you remember? And then you had the B field. You generally have the B field go into the board, so the force in the end would go to the right. And then when you enter here, you'd have a B field coming out, so then you can move up. Or, correct, sorry. And here B field's coming out, right hand, sorry. Here B field will be coming out, and here B field will be going in.
Okay.
If this was a proton, because then you use the normal. Okay? Because F is V cross B, you know the V is coming in, cross B, and then you get the force, the direction of the general force. Yeah? Okay. So to find out if it's either going to go like that or like this, you do, oh, yeah. And I think it would do this. Something like that.
I guess my problem is when it's going from A to C, I know it's going like, it's not going straight, right? It's going like diagonal.
It's not going diagonal. It's going at a like curvature.
Okay.
So it's like a semi, I guess a semicircle, right? You
Okay.
call it that. So think that at some point, let's just say B, I guess, would be the center of the whole thing.
Mm-hmm.
It's just going to travel around in a semicircular path. Mm-hmm. That's the same thing you saw in the homework over here, where it's just going in a semicircular path, and because the B field changes, it then continues on a different path. Otherwise, it could have just gone like this.
Mm-hmm.
Right? So it never takes a direct path. A proton or an electron never takes a direct path in the B field from one point to the other. It always goes in like a curve. If you have any more, like if this is still confusing, just go back to this homework. I forgot which one it is, but I'm pretty sure you guys will remember. Probably B field, to be honest. Go back to this homework, and then you'll see what you guys did. Let's see.
Okay. Can you explain why you draw the F? Why is it?
Like this? Okay. F is V plus B, right? So F will determine which way it will go. Right, so if you have the general velocity will be to the right. Right, because if it starts off, it will go to the right, and then it will take some curve. Okay? And because it's an electron, we'll use our left hand to keep it normal. So you go V and then cross B will give you a force. Now that force will pull the electron towards it, meaning the force will push down on the electron. So if the force pushes down, it will take a path like that. If this was a proton, right, you have a V up. If it was a proton, it would take a path like this. Because then you have your V, B, F would push it up. Remember, for proton, use the right-hand rule. And for electron, you use the left hand. Or opposite right hand. Okay. Next question, anybody? Is this anybody, by the way? No, right?
Mm-mm.
So, okay. Next questions? For the exams, like you saw in the first one, it's very similar to the homeworks. So whatever chapters he told you today in class, or whatever units, it was like what, 7 to
9 to 17.
9 to 17? Yeah, just go over the homeworks for those. I don't think he's gonna give like super hard ones like slabs. I hope not.
Now, he told me, I went to him for hours and he told me that anything if you're with an example hard problems, he won't put them on the exam. On some of the slides, people like example hard problems. He normally doesn't put them on the exams.
Yeah, that would be ridiculous. So it's 9 through 17. So just look through those, go through the homeworks. I always say keep a notebook to do the homework problems in, so you can always go back and remember what you did. So it becomes easier when you're trying to study for an exam.
I have a question about more let's do tomorrow. What was number 2? Rotating triangle.
Tomorrow is, wait. Oh,
Unit 17.
huh?
Unit
Yeah.
17.
Rotating triangle? Oh, we did something like this last time. Yeah. You had something like this, where it was, you had, it was like this. In one field, right? Like let's say it's coming out, and they give you a second one where they rotate it and it goes like this. But the field is going in. And this was a current carrying wire. Don't you remember? It was very similar to that. Yeah, okay, but what's the question? Go ahead.
Number 4. I don't understand why the current is positive.
Number 4. Okay. Rotates levels. Makes one complete rotation in 1.4 seconds. So that's so 0.7 seconds. It makes half a rotation. So it makes 180 in half. At 0.5. 0.5. So so it's still like that. Okay. Okay, why is it a positive thing? Goes in the negative y direction. H, so it's in the negative y direction. Can I erase this so I can draw the?
You go ahead.
Okay, field is like this. And let's say this is H. So at time 0.525 is what I have, right? And I'm getting 1.4 seconds for full rotation. So 0.5 is just beyond half. Or wait, just 0.7 for the full, 1.4 divided by 4. Yes, just beyond. It'll be something like this. Not exactly flat, but just a little out. You know what I'm saying, right? It'll be something like that, okay? And this is H, and whatever. What's the asking? We're saying positive will be if the current flows in the negative y direction in the segment H. So this way means positive. So current will flow like this. Clockwise. Yeah? Okay. So they're asking why this is positive. They're saying okay. So if you start off with this, start off here, and this is here. So, okay, I think it has to do with the mean, right? So when it starts off like this, initially, okay? This is H. Okay? If the V field's coming out, and it rotates like this, right? It rotates coming out of the page and then across.
Yeah.
Right? Like this. Right? It goes like this and over.
Mm-hmm.
Okay? It goes like this and over. The V field's coming out. I would take the right hand rule, right? Go like this, and then mu comes out. Okay? So if mu comes out, then okay, so if the mu comes out, actually, I'm not exactly sure. Ask them in office hours or something. Okay, but I think it's because if the mu comes out of the field, it's directly in line with the B field, right? And that will cause it to turn a little bit. And if that turns, then when you get to this point, then the current goes in that direction. I think so.
I just wasn't sure when to use the right hand rule. Because I got a negative number for EMF, so I used the negative number to find the current, which is in the negative number, so.
Yeah. I'm not sure, sorry.
Can you go over the first checkpoint problem?
Local current.
Yes.
Okay. Okay. What equations do you have for this? Like for magnetic flux? I forgot my notebook, or my binder, sorry. What equations do you have for magnetic flux?
Integral of P.TA.
We got the, yeah, okay, that's one, right? But is there anything with like mu or current or anything like that?
Flux. Or asking flux.
No, for,
For me.
okay, so I think for this one, it's because if you go counterclockwise, like for D, right, then your mu goes up, right? So all the EMF would be up. So it doesn't cancel out with the magnetic field. And then if it's clockwise, it will be down, right? The EMF would be down. That will cancel out with any B field that's going through it, any field that's going through the loop, because it's in the opposite direction.
Why?
It's like, you remember today in class when you did the GFCI, you said that there's two wires running? Remember? He showed the little thing that goes in the wall for when people plug in their hair dryer, it doesn't like.
Yeah, okay.
So there's two wires, and then if the current, there's two currents going in opposite directions, cancel out the field, and two currents going in the same direction, there would be a field inside the wire. So that's the same deal here. Where if you have your, you know your EMF, right? The direction of your EMF goes by the current.
So the same direction. Over.
Yeah, like when you curl your fingers, right, around your coil or whatever, around the direction of the current, right, your generated EMF will be in the direction of your thumb, right? So if the field is coming from the bottom, and if your EMF is going to the bottom, they'll both cancel out. Because both fields will cancel out. But if your EMF is being added to the field that's coming in, that will result in like a strong field. It's not going to cancel out.
Can you go over all the right-hand rules that we need to remember? Because like EMF and current, like when you curl your finger, all the current, the thumb indicates the EMF, right? And then in previous chapters, they're like current and B field.
Current, B field, mu.
Yeah, mu. Wait, the mu is also thumb. Okay.
F for F equals V cross B is also thumb. Okay, yeah, I can go over as many as I remember. I don't have, this will be a bad day to forget my paper. I'll do it, remind me next Tuesday if you guys come. I'll go over it again because then I'll remember to bring my binder. But I have all the equations in there, so I can go through and see which ones would apply. But as far as I can remember, I'll go through it, okay? So do you want me to write it on the board or just like talk about it?
Your equations are helpful.
I'll do as much as I can remember. Okay. Okay, so let's start all the way in the beginning.
From chapter 9.
Chapter 9. Yeah, let me go look at chapter 9 and see what it was about. So I can see. Okay, electric current. You didn't really need anything for electric current because electric current is all resistors and stuff like that. RC circuits, no. Magnetism, yes. So force and torque on currents, right? That's where you need right-hand rule. That's where really we got into it. So you know that when you have a loop, okay, and if you have current flowing in, let's do it like this. Let's draw it like this. Okay, you have current going that way. Okay, if you have current flowing that way, then you know mu, which is the magnetic dipole moment, is perpendicular to that field, right? To mu. Mu. It's magnetic dipole moment. It's perpendicular to the field, right? And no matter what, like, and it's given by the right hand rule. Okay. So you know if you have something like this would be mu. Right? And so when you put something like this in a generator, or when you have a B field acting on it like this, you can do mu cross B and find out, I think, E or something like that. I don't remember the equation. It's, but it was mu cross B gives you something. I forgot. Okay? So that's how then you can do that. I think it was torque. Yeah, torque equals mu cross B.
Yeah.
Right? The torque equals mu cross B. Right? And remember, this is all in 3D. So it's very difficult to look at it at 2D and kind of determine which way the torque goes. But if you go like this, okay, now it becomes a little easier because then you have a 3D thing. So you know that mu goes this way, right? It goes out into this plane. B goes straight up. So you go here, cross B, you get a torque that's in the torque. Right, so that's one equation. That's one thing where you have to remember how to do the right hand rule for me, especially for torques. When you're given, and this was a homework problem, I believe. We did whiteboard on this in class. So he might ask something like this. So just go through, this is unit, yeah, 13. This is
13.
This is unit 13.
Hold on.
Yeah, I have it on this 13. Right, so that's torques.
Is this a checkpoint question?
No, she's just asking like, what are the general right-hand rules for some stuff?
Okay.
So I'm going through the list and seeing what I can remember.
Okay. So torque.
So torque equals mu cross B, and mu is given in the direct. Put your fingers in the direction of the current of a loop, and your thumb gives you the direction of mu.
And what's mu again?
Magnetic dipole moment. That's just what we call it. Now remember, mu wants to be in line with the B field, right? So if mu is parallel to the B field, there's very little potential for it to want to move. But if mu is directly opposite it, it's going to be a lot of potential for it to want to come back. Right, so just remember that in case he asks a question like, which one has higher potential or lower potential based on the angle it makes with B. And I always take the shortest angle. So here, let's say this is like 30 degrees, right? You would just pick 30 degrees. You wouldn't say 270 or 330. You wouldn't go all the way around. You just pick the shortest angle between U and B. Okay? So that's that.
So you mean the loop will rotate this way? So it's will align with E.
Yeah. Like that. Like this part will go in. Okay? So that's torque. And then right hand rule is also given for F equals IL cross B, where I is the current. Wait, IL, yeah. For a wire, both on a wire, I believe. Or is it IV cross B? I think it's IV cross B. IL, right? IL cross B. I think this is for force on a wire, from a conducting wire on a point or something like that. Okay? Right hand rule is also given like this, because remember, when you have a wire, and you have a current going in the wire, that generates a field around it, a magnetic field around the B field. Now, the B field will be given in the direction of the current. So you put your, so it's essentially like you're wrapping the current, you're wrapping the wire, you're holding the wire. Whichever way your thumbs point is the way the current goes. So on this side, the B field will be coming out, right? And on this side, it'll be going in.
So this is the second right-hand rule.
I mean, there's not like a specific number of right-hand rules. I'm just doing stuff I can remember.
Okay.
So I guess if you want, yeah. So the other right-hand rule to remember is the B field will be given by the direction of the current for a wire. And it will change based on what side you're on. Okay? And this can also apply to a sheet, an infinite sheet made up of multiple wires within this wire density, given a wire density of, let's say, like, 10 wires per meter or something like that. Like this right here. Okay. You have all these wires, right? And it makes an infinite sheet. All the wires go back into the page. Okay? It makes an infinite sheet. Now you know the current in the wire, let's say, goes in. Okay, if the current goes in, then you know the current goes in the B field here. Yeah, current. The field here would be this way. Yeah, the force here would be that way, and the force on top would be there. Right, for an infinite wire. It's the same thing as the current. So it's the same thing as you take all the currents and you can do the same rule, and apply the same rule to it. Okay, so that's the same thing for the infinite sheet. And what else do we have? Didn't we just do this yesterday? V cross B, something? Yeah, for this, F equals LV cross B, right?
Yeah.
So we did this yesterday. Okay, and this is for a loop entering the B field. Remember you asked me the question when it was like this?
EMF.
Yeah, that's EMF.
Yeah.
But again, the right hand rule applies for the direction of the current. The current can go this way, right? Or the current can go this way. And the loop, we have to know the V cross the direction, and then you'll get the charge separation. Right, so let's say that the velocity is going this way, you enter the field, so velocity cross B, so all the positives will get up over here, and all the negatives will go here, and the current goes from positive to negative, right? So in this direction, the current will be going like this. Right, so you need to know that. Okay, yeah. We have a loop entering a B field. Right, where the field is, let's say, coming out. Okay? So you know V cross B will give you F. Okay? So V is coming in, B is coming out. V is going to the right, and B is coming out of the page. So your thumb goes down. Right? If your thumb goes down, that means all the positive charges will gather at the bottom, and all the negative charges will go to the top. Right? So then all the positives will gather here, all the negatives will gather here. Okay, and we know that current goes from positive to negative.
Oh, yeah.
Right? Current will go from positive. That's why in a battery, when you draw batteries, draw a battery. This is the positive, this is negative. You always say, okay, this is resistor 1, resistor 2, capacitor 1. Then we always say, okay, we know that the total current that will ever enter the system goes through resistor 1 first. Remember that? Because current will always go from positive to negative. Yeah.
So how do you know which way it goes? So if you know that all the positives go at the bottom and all the negatives go at the top, how do you know if it goes like this way?
Yeah. If all the positives gather here,
Right.
all the negatives gather here, I think the current will go this way. We go from this.
When it's entering the beacon?
Well, I mean, once it's already like this.
So why wouldn't it go the other way?
Because that part is already inside the field.
Oh, okay, got it.
Okay, and remember, for these type of problems as well, for EMF problems, you take the length of the part that's already in the field. So if this was like you asked me, right, or it would be like this. For a question where you ask me like this, okay, she asked, well, when you try to find whatever equation, do you use this distance or do you use this distance? Right? And you always use the distance that's at the edge of the B field. Okay? So in this case, this distance is at the edge. And this whole square is already inside the field. So you will use this distance when you're using your equations for L. Right? We worked on this yesterday.
Mm-hmm.
And then same thing for that other problem that we did, where it was like this. Remember that one?
Yeah.
So for this one, they say, okay, this side is 3 times this side. Okay, and this was on the homework yesterday, you probably remember. And they gave you something like this. So they asked which one has the higher EMF, which one has a higher voltage. Well, this side you do 3 times minus 1, so you're left with 2x, and here is just x. So this one has the higher. because both are on the edge. Okay, and then you subtract them because see this gap? You would subtract to find this. Okay? You don't add the two. I mean, you would kind of get the same answer, but like in case the numbers are like 4 or 5 times, then you might not get that. Okay. So make sure you subtract this one from that. Okay. So that's that, and then what else? It's mostly for current, to be honest. Right-hand rules, a lot of it is current. Current and B fields. Torque, new, F equals L cross B, torque equals mu cross B.
That's like QV cross B.
QV.
Oh, magnetic force.
Good.
Let's see. Let's see. I'm interested in going through one more exam question.
Sure. We have about 5 minutes. Let's see how fast.
Let's see. I want to go over the last one.
I'm ready.
Yes.
Okay. Okay. Here's this one. Square, moving to the right. This is the exam thing. Okay, so you know that, okay, now what's the first thing you can do is you know which way the B field is gonna go, okay? You know if the current's coming down,
Mhm.
B field at this point will be coming out,
Right.
right? So here the B field will be coming out, okay? And you know that it's moving to the right. Wait. Okay. So coming out, moving to the right, so here's its velocity, here's the B, I know force equals across B. Right, so positives will gather here, negatives will gather here, so this is the flow of current.
Does it have anything to do with B feels stronger on the left side than the right side?
Well, it's a uniform field, but I think it's, I think it says that, doesn't it? No? No, it doesn't say that. No, but okay, so the other thing is, you see here, these will be positive, these will be negative, right? If the current flowed this way, it would go from negative to positive. Right, at least from here, it's going positive to negative. But then here, it has to go back because it's in that field.
Wait, so it's going from
I'm thinking this way.
clockwise?
Yeah,
The loop is
the current,
the current in the loop.
I think so, yeah.
So it's positive to negative, right?
Positive, negative.
So you're saying it's going this and this way?
No,
Oh,
I think it's going clockwise.
okay.
So you know, just like there's like force equals IL cross B, and then force equals V cross. Those are two different, completely different.
Yes.
Okay.
The IL cross B, or wait, IL cross B, right?
Yeah.
That would be used for something like this.
Would be used.
Yeah,
Okay.
because here you have L, right, a length, and you have a current inside the loop.
Okay.
When you have F equals V cross B, you would use that for something like what we did on the homeworks and stuff yesterday.
Okay. So you can't use it for this, even though it's moving.
No, because you're given like a current, you're given distances, you want to use equations where you have more knowns. Right? So this would be used for something like that problem we did where you're going like this. And you're coming in with the velocity, you have some B field that's going this way, it's going this way. We would use this equation for something like that.
Okay.
So how do you know if it's clockwise?
I think it's clockwise because well, V cross B, there's all the positive charges here, and then that will move.
So it's not on this side?
Is that one counterclockwise? I don't think so.
Then how do you know? So the positive charges are all at the bottom, and the voltage on the left side is higher than the right side. Not the voltage, the E field?
Yes, because it's closer to the
The
current
wire.
carrying wire than this half.
So it's clockwise.
Yeah, I think it's clockwise. So,
Is it clockwise?
I think so.
Okay.
I think it's clockwise.
I just don't get it. So what equation did you use to get the current direction?
Well, just use the V because you're moving to the right, and then the B that's coming out of the string.
Yeah.
That will give you an F. Then all you know, then all the positive, then you know that the positive triangle will be towards the bottom, and the negative will go towards the top.
Yeah, I got that part. But how do you know if it's going this way?
This way, I'm not 100% sure, but I think it's going this way.
Yeah, but how did you determine that?
Oh, because if it would go here, it has to cross the whole, goes here, then it crosses the whole loop. Like the current starts and crosses the whole loop. I'm not 100% sure on this one though. I'm sorry. I haven't done these in a while. But yeah, just ask him in office hours or even in class, just ask him to go over these. Will he do a review Monday in class?
Yeah.
Yeah, just ask him this question. And if I'm wrong, well, I'm wrong.
It's fine.
But not then, hey,